Right, so Module 8 really is just a continuation of the last one, where we're going to get a little bit more practice problem solving with math functions and think a little bit more about testing our code, making sure that we get the right answers, and how to go about doing that. So really it's just we're going to go over a few problems and code them up. So programming example 7, I'm asking you to collect a single dimension from the user. So one value. We'll call it A. We can really define it as anything that we want. And from that one dimension, I want your program to print out a variety of areas. The area of a circle, the area of an equilateral triangle, a square, a pentagon, and a hexagon. So a total of 5 different outputs based on the same individual input. So what I want to stress here is how do we trust our data when we calculate it? Certainly, if we use the power function, for instance, we can calculate a squared to get a square back. That's fairly straightforward. And of course, we can plug in numbers that are easy for us to know, right? So we can test the code for the area of a square, for instance, by just typing in 3 and knowing that it'll come back as 9. For the other areas, things are a little less clear, right? So it might not kind of roll off your tongue what value the square root of 3 is. What is the square root of 3 over 4? If you don't know those values, you can't really trust your data and really trust that what you've done is accurate. And even though some of these equations looks fairly simple, it's not out of the realm of possibility that we can certainly make a mistake. Right? So we're going to start by, I'm just going to start by programming in the area of a circle, which we've done in the past. And I'm going to use a search engine. I'm going to use Google, for instance, to find some online calculators just to plug in some inputs and make sure that my answers are starting to match up with answers that I can get from other sources. You always want to check your work against something that somebody else has done. Hopefully you can find a reference implementation of something. Certainly, you know, as you learn to program and you do larger programs, you'll be writing programs that nobody else has written before, and testing becomes much more of an art then. And we will touch upon that as we go through the semester. So I'll start out just by implementing the first part of this, and we'll do some testing. So I've begun the program. I'm going to ask the user for a dimension. I'll call it A. And because it's going to be used in the area of a circle, the area of a square, or the area of several different things, I'm just going to call it dimension, sort of a generic label for it. We will avoid units here because really the units don't matter. If the user types in 2 centimeters, the area will be printed out in centimeters. If the user prints out 2 feet, the area will be printed out in feet. So it's implied that we're using the same dimension to calculate the areas as the input. So we don't really need to specify specific input or specific units here. So the area of a circle, and I'll create some output variables. Just call it circle. The area of the circle is going to be circle equals pi times r times r. And of course we don't have those variables, right? So in this case it's going to be a. A is the dimension that the user is typing in, and pi we really need to define, and we've done that before. We use a constant. And this is probably good enough of an estimate for our purposes. It's probably not that great for something where you really would want some good precision with it. Now we could have also written this, now that we know about the CMath library, we could have also done pi times the power of a to the second power. Both of these would be equivalent. Pi times a is the same thing as pi times a squared, which is really the result of this function. Which one you choose to use is up to you. Certainly if I had a to the 5th, I would do power a5 rather than typing 5 a's out. Squared, maybe even cubed, I might write out long form like this, but not always. Okay, so let's print out our area. And build that. And we'll go over and we'll give that a run. So I'll type in, let's say 5. Okay, so when we look at 5 and we see the area come out as 78.5379, if we think about 5 squared is 25, 25 times 3.1459 is roughly 3 times 25, which is 75. So the number seems pretty reasonable. That's a pretty easy one to get a good guesstimate on whether your numbers are correct. And of course we can test some real easy ones, like maybe an area of 1 would come back as pi. But if we don't want to leave things to sort of just guesstimation, we can always double check it. A lot of these type of questions are very easy to get a real answer to just online. So if I just type in area of circle, I immediately get a circle calculator. And so I can type in 5 and make sure that I see 78.54. And if I look back at my number, 78.5397, certainly that rounded to 78.54. And I can actually go through and test different numbers. So if I type in 80, I've got 20106. Go back to my program, type in 80, and I got 20106. Okay, so there's really never any excuse in any situation when you're writing a program to output numbers that are just not right? To make a mistake and not be able to pick it up, especially when we have situations where the formulas are readily available online. Now you might say, well, I could have just calculated this by hand and I could have found this out. That is true, although, frankly, I would usually allow a fairly reputable source, Google's a fairly reputable source, to calculate it for me and to make sure that my numbers match up with it. Okay, so let's continue and look at the next formula. And so this one's a little bit more tricky, right? So we've got the square root of 3 divided by 4 times a squared. Right, so let's go over and maybe even before we even write this code, we can find out how we can test it. So area of equilateral triangle is pretty easy to find. We've got our formula. It's certainly the same formula. In fact, I think I took it from this presentation on the slides. And we can type in some test values. So 5, for instance, should be 10.83. So given that might be our first test case. So let's go in and implement this. I'll have triangle. It's the only type of triangle we're calculating, so I'll just call it triangle. Triangle equals the square root of 4. Let's go over here. It's going to be the square root of 3, square root of 3 times a divided by 4. So we can do square root 3 times a divided by 4. We could have done also square root 3 divided by 4 times a would really be the same number. And so we'll use our test case. And we see 78.53 come out and 10.8253, which rounds to the same thing as the 10.83. If we want to double check with a couple of different ones, maybe 9.5, 39.08. If we look at our program, type in 9.5, and then we get 39.0794. Right, so that's looking good as well. And now we just start repeating this process, right? So for each one of our outputs, we probably want to get some test cases and check it as we're writing the code. So floating back area of a square is actually really easy. Right? So we can say square. We don't need any math libraries for this. Square equals a times a. And this is one where we could, of course, go back to Google and check it, but the square is relatively easy to check just in our heads. Of course, we should get 9 and get 81. All right, so continuing forward, next one. This one's a lot more complicated, right? So we've got the area of a pentagon being a fourth times the square root of 5 times 5 plus 2 to the square root of 5, or 2 times square root of 5 times a squared. It's quite a mouthful. This is something that we probably want to immediately start to look at in terms of test cases. So let's bring up Google here. Area of pentagon. Right, so we can see that. So let's type in our standard test case. 5 is 43.01. Right, so 43.01 for 5. We can actually write that down. So we remember it. Let's put in the pentagon. And now let's start calculating this. Right, so the first part of this is just a 1 times 4. We can put that in pretty easily. Multiplied by the square root of a big term. Right? And so let's go through and look at that. Let's actually calculate that out first. So it's 5 times 5 plus 2 to the square root of 5. So I'm going to create a temporary variable. Make it 5 times 5 times, and keep looking at this, 2 times square root of 5. And now I'll do square root of temp. So there's the entire term underneath there. And if we look back at the formula, after we do that, we're going to multiply it by area squared. All right, and we'll go down and we'll print that out. And give it a run. Type in our test case, and right off the bat we see there's an error. Now that's an easy one. We certainly, even without Google's help of telling us that the area of the pentagon should have been 43.01, we would have known 0 was wrong. Whenever you see something come out to 0 and you've done all this hard work with an equation, one of the things that you should think about is integer division. Is it possible that one of these terms got set to 0 accidentally? So if we look back at this formula, and there it is, all right, remember that all of these are multiplication and division. They all operate on the same level of precedence. Now you might look at this and say, well, wait a second, the 4 times the square root, that's going to be a double because square root returns a double. But remember that everything happens left to right at the same level of precedence. So knowing that the division, the multiplication, and all the rest of the multiplications are at the same first level of precedence, if we follow this left to right, 1 divided by 4, 2 integers, is 0. And then at this point, I'm just multiplying 0 by anything is going to be 0. So that's our first mistake. Let's go ahead and build that. And type in 5, and we get 66.0857. Now that clearly is not a right number, right? So we know that we've got the wrong number here. And now we're going to have to go back and double check. Now, first thing I would do is maybe just double check that I typed this number out right, the 43.01, make sure that I interpreted that right, and I'm not remembering it wrong. But certainly the 66.0857 did not match up with what I wrote down over here. So we'll go back over to Google, type in our 5 again, and just confirm, yeah, it is 43.01. So now at this point, I mean, always make sure that you've gotten things from a good source. It is conceivable that maybe what you're testing this against is wrong, but of course I think it would take a little bit of a stretch of imagination for you to make yourself believe that Google has messed this up and you've got it right. So it's very likely that we've got some sort of a typo or a formula has been misrepresented. So let's look at the formula. I'm gonna grab that. And I'll pop this over on our screen. Okay, and let's go and look at our code. And this is really the formula that we were using. And now let's just take a look at this and try to figure out what really has gone wrong here. So looking at the equation, we probably the first part that I would be concerned with was this 1 over 4. We've already checked that out. We've already kind of confirmed that we've converted that to doubles, so that is good. The complicated part of this formula is certainly this interior of the square root. So I probably want to check out how I calculate a temp. Another possible issue might be that maybe this line should have been a little bit longer. If that was the case, certainly we could test that, right? We could put the square of a inside the square root and print it out and see whether it came up right. So those are our places to start to look. And again, since we've already looked at the 1 over 4, I'll go right over to here. And if we look closely, I can see the 5 times 5 plus here, and accidentally I typed a multiplication sign. Right? And there you go. That's going to be the problem. Right? So that multiplication sign is what's causing our numbers to be incorrect, likely. Now, it does not necessarily mean that that's the only mistake, right? So we definitely want to change it, and then we want to test it against our test case again and make sure that that fixes it. I've written lines of code myself that have 4 different mistakes in the past. So we certainly are going to need to keep checking until we get those numbers right. So let's go back to the code. We'll change this to 5 plus. Easy mistake to make. Go back here, we'll rerun the program, we'll type in 5, and now we get the 43.01 that we were looking for. All right, so that number is correct, and it looks like we've got the pentagon corrected. And I want to just pause for a second and point out the importance of having that test case. Right? So we've implemented the area of a circle, the triangle, and the square, and those have gone fairly smoothly. Very easily, if I was to sort of not really be testing all that much, I might start to get lulled into the belief that I'm not going to make a mistake. If I look at the area of a pentagon with a dimension of 5, 66.0857, unless I've been taking an enormous amount of geometry classes, that seems relatively right to me. There's nothing that seems alarming about that 66.08. The reason I knew it was wrong is because I had checked it ahead of time and I already knew what to expect. And that really that's a good habit to get into. Try to figure out what you expect to see before you actually even run the test case. So you can immediately see that problem. Never just sort of trust these numbers. If you were to ask me 20 minutes ago what the area of a pentagon is and given me 2 choices, 66.08 or 43.01, I would have had no idea as to which one was correct. Right? I only knew which one was correct by testing it independently of my program. And I was able to catch a very simple and certainly very bad mistake. All right, so on to the next one. If we look at this, we've got the area of a hexagon. This one certainly is a bit easier. We can do 3 times the square root of 3. Now, notice that we have the square root of 3 already. We calculate it as the equilateral triangle, and we'll talk about that shortly. Let's add our variable. It is going to be 3 times the square root of 3 divided by 2 times a times a. I think that was the formula. Let's just double check I got that right. 3 times the square root of 3 divided by 2 a squared. Okay. I can get rid of that test case. Before I run it, let's check. And obviously this is a pretty easy example in that Google already has all we need for most of these questions. Sometimes you're going to have to think a little bit more carefully about how to get the answers that you're going to test against. I keep using 5 as a test case. I don't really know why. I can use 6. It doesn't matter. Let's use 6. 93.53 is what we should get. So let's build. And we get 93.53. 93.53. All right, so now let's look at the code a little bit. And notice that I mentioned that we calculated the square root of 3 twice. Ultimately, the amount of time that it takes to computer to calculate the square root of 3 is quite small. It's probably not that much of a concern of ours, but we certainly are kind of calculating the same exact answer twice. And the square root of 3 inside that function, there is actually C++ code, and it involves a loop, which we'll learn shortly. And it takes, 20, 30 probably instructions for the CPU to figure out what the square root of 3 is. Now, if I wanted to save that time, what I could do is I could say, create a variable, square root of 3 equals square root of 3. And then instead of recalling that function each time, simply replace it. Instead of we calculate it, maybe 20 or 30 different CPU instructions will be required to calculate the square root of 3, but now each time I use it later on, it'll be essentially for free. I have the answer already. Certainly won't be a noticeable difference in speed in the program that we're running now, but if I was actually going to replace thousands or hundreds of thousands of calculations of the square root of 3 with one single call, that performance difference actually might be quite noticeable. So this is a common technique that people will use to help their programs run a little bit more efficiently. We always want to check whenever we make an optimization. This would be considered an optimization. We always need to check that nothing has broken. That's pivotal. So we see that the 93.5307 is the same as well. We also probably want to make sure, if we go back here, the square root of 3 was in the equilateral triangle. We also want to make very sure that the equilateral triangle didn't change. Having all of these, retesting everything is called regression testing. When we make a change, we want to make sure that we double check all the things that used to be correct and make sure that they haven't regressed. Make sure that something that we've changed in our code is not broken, something like the triangle, from working now. All right, so at this point, I think we're done with the area question. We can maybe neaten up the output or something like that, but for all intents and purposes, we're complete. So the next programming example is not based on geometry or physics, but it's back to our the domain of money and dollars and cents. And in this program, we're going to calculate the amount of money in a savings account after 1 year. And that actual formula, or the amount of money you'll have in a savings account, depends on a number of different factors. First off, it depends on your initial principal. So obviously, if you have $100 at the beginning of the year, you're going to have a lot more money than the person that only had $10 in the bank account, assuming that everybody has the same rate of interest. So principal causes that to change. The interest rate certainly is going to be different. Somebody who gets a 2% interest rate on a savings account will have more money at the end of the year, all things being equal, all other things being equal, than somebody with 1% interest on their savings, or somebody who has a 10% interest on a mutual fund or some sort of stock fund would certainly have a lot more than a traditional savings account. The other thing that we might not be necessarily thinking about all the time when we think about banks is the number of times compounded. So the number of events where the interest is actually applied. Sometimes interest can be applied yearly, once a year at the end of the year. Interest on $1,000, if you're earning 1%, would be $10, and that would be added at the end of the year, and you'd have $1,010. If the interest is applied monthly, though, you will actually get the first little part of your interest that last day in January. So $1,000, you're earning 1% interest. You're going to get a 1/12 of that $10. So I guess 80 cents or so, somewhere around there. That 80 cents is going to be added in January. Now the reason that affects everything is that February's interest payment of 1/12 of 10% will be computed not on the initial 1,000, but on 1,080 cents. So it'll be slightly more than it would have been normally. So the number of times that the interest is compounded, whether it's monthly, whether it's weekly, whether it's daily being the best, because you'll have the highest rate of growth, will dramatically alter, or can substantially alter the amount that you'll end up with after a year. So all that aside, we've been given a formula, right? The total amount after 1 year is equal to the principal times 1 plus the rate divided by the times compounded. Right. Now, I don't want to ask the user in terms of monthly or daily interest rates. I'm just going to ask them for a yearly interest rate, and that's typically what a bank would advertise anyway. In addition, I could actually, I'm not going to do this right now, but what I could ask is specifically for the user to type in daily, monthly, yearly as different options. But for now, I'm going to ask them explicitly how many times is the interest compounded each year. And I'll give some examples. So if it's monthly, type in 12, something like that. So in this program, I've got a few different inputs, right? I know that the principal the user is typing in, the user is typing in an interest rate, the user is typing in the number of times compounded, and then I can calculate the rest of this formula. All right, so I'll flip over to Visual Studio, and I've already started up the program a bit. I know that because I have a power function involved right over here, I probably want to go right away and include CMath. And now let's go gather our inputs. So principal, I'll call it yearly rate. If we think about times compounded, so yearly rate can certainly be a double. Principal could certainly, it's dollars and cents, that should certainly be a double. Times compounded, it's important to recognize that really that should be an integer, right? We're not going to compound interest 12.5 times per year. It's going to be a whole number. And now I'll go through and get that data from the user. Prompt them for dollars and cents. I'm going to prompt them for a yearly interest rate. I guess that's APY. or APR, depending on how, I think there's some technical differences between those two terms. I'm not going to worry about that too much right now. And read that in. And finally, C out, enter number of times interest is applied per year. And you might actually even want to, let's see, say 12 for monthly. As an example. It's always good to give the user a little bit of an example so they can verify their understanding of what you're asking them to do. Before doing the calculation, let's just print out the output, the input, reiterated again. So principal will be in dollars. We'll print out the yearly rate. And of course, this brings out a good question. Is that yearly rate entered as decimal numbers or percentages? If the user types in 7 here or 3 for a yearly interest rate, that should come out as 3%. Now in our formula, and this is something that you'd probably have to verify from the problem statement, but in our formula, the interest is certainly assumed to be in decimal notation. So 3% would be 0.03. So we need to actually, we should differentiate between that. So let's put an example. Let's ask the user to type in 0.01 for 1%. Let's say example. And I always like to print it out in some slightly different way to confirm to the user that it's been understood correctly. So yearly rate, let's print out as actually a percentage. And times compounded. And I don't have the total amount just yet, so I'll leave it at that. Let's build. Switch over and run our program, so Module08. All right, so opening balance, let's say $1,000. Let's say I've got 1% interest. And times compounded, let's say 12. All right, so I get my output back, and of course I got my 1% interest rate. All right, so I've got my input, I've got the echo of the output. Let's go back to step number 2 and actually do the computation. So A equals principal times 1 plus the rate divided by t to the power of t. So we'll have an amount. Remember, we can't actually in the code calculate anything until we already get our inputs. If our calculation depends on our inputs, which most of the times it does, we need our inputs first. And that's just going to be principal times. And now our 1 plus the rate over t is going to be raised to the t power. Right, so we've got 1 plus the rate over t raised to the t power. Let's include this all in the power function right now. And it's important to recognize that this is the base. This is the first parameter being applied to the power function. Power function, recall, accepts a base and then an exponent. The exponent is t. So this is going to be power 1 plus yearly rate divided by times compounded. All raised to the times compounded power. Now that's a long equation. I might actually just take the interior here and do double base equals that and write it like this. I like to keep my individual lines of code fairly short. And we'll print out the amount. If we run this, $1,000 after 1%. If it's compounded monthly, we'll have $1,010.05. We can do a little sanity check here. $1,000, 1% compounded once a year should have been a $10 interest rate. We'd get 1% of $1,000 at the very end. We got a little bit more if we did it monthly, not quite that much. If we did this daily, $1,000, 0.01%, 365 days a year. Well, it's pretty much the same. I'm guessing that we probably have a little bit left over out here. Let's give it a little bit bigger number and test the difference between monthly and yearly to make sure. I'm certainly not going to assume that I've got more significant figures here that I can't see. So let's do $10,000. Let's do 5% interest, and let's do it monthly. All right, well, we get $511.60. Let's do $10,000, 0.05, 5%, and let's do it 365 days a year. And yeah, so now we do see there is certainly a difference, a minor difference, but there is a difference nevertheless in terms of the amount of interest you will get. So is this good enough? Are we satisfied that this is enough? Well, it's fairly easy to, you can input fairly easy numbers to understand. You can see that there's a relationship between monthly and yearly, but we go online and find out, type in a savings account interest rate calculator, and they're all using the same equation. So that would be an excellent source to double check all of your work. So to conclude this, we've got our correct number. Certainly we've talked about this in previous modules, we might want to make things a little bit more user-friendly. So we could, like we've already done, we've certainly clearly explaining what we're looking for. Things like explaining times compounding, for example, 12 months. That's an important part of our prompt. We've told the user that we're expecting 0.05 for 5% or 0.07 for 7%. We could certainly adjust that. We could certainly change that. Right? We could actually ask them to just type in 1 for 1%. And we would, instead of doing anything with the yearly rate, when we're printing it, we would probably do something like this. Yearly rate divided by 100. So if the user types in 1, I will read that in, but I'll transform it to be a rate that I can actually use. So getting a changed rate, a rate that is actually divided by 100, allows the user to type in things a little bit more naturally. It doesn't really affect us. We have to work just a little bit harder. But again, $10,000, 5% interest, 365 days a year. We get the same exact number, but now the user can type in 5 instead of 5%. So all of those little lessons are important to remember as we continue.